Okay, I think we can get started. Hello, everybody. I'm Saman Zunus from Georgia Tech School of Cybersecurity and Privacy. So today we have 3 excellent papers on information flow for robotics, operating systems, device driver implementation within trusted execution environments, and then fuzzing firmwares. So the first paper is by Nishit Pandya. He did this when he was at IIC. He's currently a PhD student at UCSD, and he'll talk about information flow for ROS robotic operating systems.
Yeah, thanks. So I'm going to talk about my work on decentralized information flow control for ROS2. This is work that I did while I was at the Indian Institute of Science, along with my co-authors Himanshu, Gokul, and my advisor Vinod, Ganapathy. So robots are growing in scope, and they are sort of slowly taking over lots of spaces. And when I say robots, I don't just mean personal assistance robots. I also mean fleets of warehouse robots, or military robots, or swarm drones, or even autonomous vehicles, which all kind of use robots in some way or the other, right? So things that interact with the physical world in some form. And a lot of these robots do a lot of very common tasks, depending on the domain and so on. So over the last several years, there's been a growing ecosystem of companies which make and develop apps specifically for robots. So these are just some of the companies that I found. So they make apps which are built to do tasks for robots, but for specific purposes. So for instance, some of these companies make image processing pipelines. Some of them make cloud monitoring platforms. Some of them make hardware acceleration software, that sort of a thing. And so you have this growing collection of companies which make different apps for robots. And if you're developing a robot, you'll basically just you'll try to plug and play a lot of these things and get them to work on your robot, and you have ready, right? You have it ready. So how do these apps all communicate? So the common platform they are built on is called the Robot Operating System 2, ROS2. It's a bit of a misnomer because it's not really a robotics system. It's a collection of user space libraries that facilitate communication between all of these apps. So how does ROS2 work? So ROS2's primary API that it provides to developers is a publish subscribe API. ROS2 applications are called nodes, and they publish and subscribe to various topics. For example, this is a demo pipe. This is an example pipeline that I'll use throughout this PPT. So you have a node called camera, which publishes images to a topic called image raw, which is subscribed to by another node called formatter, which publishes to image high res. It's published by encoder, and there might be like a long visual pipeline going down, which does things like image localization and segmentation and deep learning and whatnot. So these are the nodes. You can think of them as processes running on a machine. And the topics are basically just ROS abstractions that help communicate the intent of or the semantic content of the messages that are being published to those topics. So yeah, ROS basically facilitates all of this communication. And one of the things in ROS2 is that it supports basic encryption and authentication facilities. But as you'll see that this basic encryption and authentication facilities are actually not sufficient for the kind of control that we might need. So the problem that we are addressing is the problem of downstream control. What do I mean by that? So consider the same pipeline where you have a camera publishing to image raw, formatter, and an encoder. But now you have a malicious logger that's trying to listen to image high res. So for various legal reasons or privacy reasons, maybe camera wants to make sure that nothing that it publishes ever gets logged into the cloud, because there are often legal reasons which disallow things like that. So, but now you have a malicious logger that's trying to subscribe to image high-res, steal images, and publish and leak it to the cloud, right? So how can camera assert control over what logger consumes? And this problem, ROS does not provide a way to address this problem directly. So the solution to this is the idea of decentralized information flow control. So DIFC or DIFC. So a DIFC system basically enhances the underlying mechanism to enable the developers to track how data passes through a system. So a DIFC system tracks data of tracks a path of data using sets of tags attached to messages and nodes. It enforces the following two conditions. A node can read a message only if it has all the tags carried by that message, and outgoing messages from any node inherit the tags of its sender. So for an example, now you have tags attached to everything, camera, formatter, encoder, and logger. And the camera wants to protect its data, so it puts on a tag which marks the semantic content of that data. In case of ROS2, it's particularly easy to put the tag because the developers have already done the work to put semantic information when they announce the topics they're publishing to. So the camera will put its tag to its outgoing messages. And because the camera wants to allow formatter and encoder to read it, it will give those tags to formatter and encoder. So it will give the read permissions for the tag camera image or to formatter and encoder, but not to the logger because it does not want the logger to read it. And once it does that, the DIFC system that underlies this entire thing allows formatter to read the message, but it also ensures that all outgoing messages from formatter and encoder also carry that T in sense like a taint that all the messages that have to carry. And the DIFC system will now stop logger from reading the messages, and then this way we camera gets some control over what happens to its thing. And so this problem is especially true in case of loggers because a lot of the robotics loggers are also used for debugging purposes. So developers often configure them to be able to listen to everything and publish to everything. And so if your logger itself is malicious, it can kind of lead to lots of data leakage, which you want to avoid. So ROS2 provides some unique challenges to enforcing such a system. So ROS2 is a distributed system, which means the sender node and the receiver node can be on two different physical machines altogether. And because the way ROS is built, the OS is completely opaque to the details of topics and nodes, and all the messages that pass through the OS are sent by the same port. So this sort of a decentralized notion means that we cannot rely on ROS2 itself to enforce the filtering of the message on the receiver, because by that time the message is already in the receiver's address space, and we don't want that to happen because then the malicious application can just read that message. On the other hand, if you want to filter the messages on the sender side, the sender needs to be aware of the state of all the receivers in the system at all times. And doing this in a decentralized way, you could have a centralized state management system that does this, but that breaks one of the core tenets of ROS2, which is ROS2 actively is decentralized. So this is one of the things that separates ROS2 from ROS1. ROS1 had a centralized matchmaking server. ROS2 actively moved away from that. They said we want to keep everything decentralized. And so having a centralized matchmaking, having a centralized service that keeps track of everyone's DIFC state would sort of be against this philosophy of ROS2. And this is why it's kind of hard to address all of these problems simultaneously within ROS2. So our key insight to this problem is that if you build a DIFC system on top of a decentralized ABE crypto system, then we can actually address these challenges. So what is ABE? So ABE is short for attribute-based encryption. Attribute-based encryption is a generalization of the usual public key encryption that we see in all our TLS connections and everything. And it generalizes this in the following sense. So in usual public key encryption, you encrypt for a specific user A. In attribute-based encryption, you encrypt for different attributes that people may carry, right? So your attributes could be a doctor and on duty. And so you want to allow only the doctors who are on duty to read that message. So you encrypt in public key encryption, you encrypt with the public key corresponding to a user A that's specific to that particular user. In attribute-based encryption, you encrypt with both the public keys corresponding to the attributes. And on the decryptor side, only the user A can decrypt in usual public key encryption because only the user A has a private key. Whereas in attribute-based encryption, all the doctors get their own decryption key for the attribute doctor, and all the people on duty get their own decryption key for the attribute on duty. And what this means is that if you encrypt with both doctors and on duty, only those who are both doctors and on duty will be able to decrypt, and those who are just doctors won't be able to decrypt. Those who are just on duty won't be able to decrypt the message. And we build up on this idea, and we say, well, in using that analogy, adding DIFC tags to a message is equivalent to encrypting with more attributes. And giving someone a read access to a message is essentially the same as handing out the decryption keys for that particular attribute. So here's how the system looked like in the usual case when we could have a DIFC system. And here's how it would look like with ABE. So the camera adds a tag key to its outgoing messages that is equivalent to saying the camera generates a public key for the tag and encrypts all the outgoing messages with that public key. And so the equivalent of camera granting a tag key to a formatter and encoder is camera gives decryption keys to the formatter and encoder. And now they have the rights to read those messages. And the DIFC system could read that message, whereas now formatter and encoder can decrypt and read those messages. And now with that, the system ensures that only outgoing messages are also encrypted with the same public key. So there's no real reason for anyone to do a state management. And logger can't decrypt those messages because logger does not have the key in the first place. So we build upon this idea, and we take the scheme from this particular paper that we had, and that's not sufficient. We need to do a bit more to build up on top of it. We need to combine it with the existing security primitives of encryption and authentication. We need some protection from the OS for storing artifacts. And once we have that, it allows for a decentralized enforcement of DIFC that works in a distributed setting, does not require an expensive setup phase, and also allows incremental deployment. So what I mean by that is that it sort of allows DIFC-aware ROS systems to work with non-DIFC-aware ROS systems without any expensive changes on the receiver side. And so we went ahead and built this system. We measured its performance on a bunch of benchmarks. So one of the things we measured was on this thing called iRobot benchmarks. So iRobot benchmarks, they basically provide a topology that's sort of supposed to mimic a ROS topology, and it forms this communication graph of senders and receivers and publishing to various topics in various loops and so on. This is one of the example topologies from that benchmark. It's called Mont Blanc, and these are the results that we got. We primarily measured latency and memory usage, power draw. These are the results that we got from our system and the specific scheme that we used. Yeah, and the results, the latency increase we noticed is primarily because all of this continuous encryption and decryption happening at every single node takes up a lot of compute power, and because this is a generalization of public key encryption, a lot of compute is spent in modular exponentiation, and that takes up most time of the process. And yeah, so over the length of a path, every node decrypts, then computes, then encrypts again. And because of this, latency grows significantly for longer paths. For shorter paths, the latency is much more comparable to ROS2, but as the length of the path grows, it goes up quadratically with the increase, and that explains the latency. And we suspect more implementational optimizations might help here. And in summary, we address the problem of downstream control for ROS applications. We basically recast the problem of DIFC into an encryption-based solution. And this encryption-based solution allows for a decentralized, distributed, and dynamic enforcement, which fits in line with the ROS philosophy. And yeah, that's basically my talk. Thank you very much.
Nice talk, thanks a lot. I was wondering, could you quantify a bit the amount of overhead, or at least in a qualitative term, say, does it increase with the number of attributes or things like this, that I get a feeling whether it's...
So the more attributes you add, it sort of increases linearly with the attributes. And each of them, the specific scheme that we used, each of them adds like 3 more modular exponentiations. Each of them, so each attribute that you add to the thing, it adds 3 more modular exponentiations. That's because that's particular to the scheme that we used. There were some older schemes that were slightly not fitting with the design that had this lesser number, but because we wanted to fit in the design, we had to go for a scheme that allows more flexibility, and that increases the cost a bit because it does 3. So basically, you do 3n times the number of attributes that you have.
And if you would select the key length that would give you like 128-bit security, how many instruction cycles would each of these steps then consume?
I'm not quite sure on the number of CPU cycles for that each of them would take, but so we did this for an elliptic curve based implementation, and yeah, so it's basically the bottleneck is the exponentiation. It's the same. So for the time that takes for one modular exponentiation, that multiplied by 3n is what the.
Thank you.
Yeah.
Any other question for Nishit? I actually have a second one. So I was wondering if the solution also supports like temporal policies, like LTL predicates, that policy. I mean, you mentioned about privacy policies that data should not leave to a particular destination. But if, for example, a robotic system, a cyber-physical platform, you may have a policy that says this should not happen before that, or these kind of the different temporal operators being in the policy predicate.
Not directly. I don't think. I mean, we have not thought along those lines, so I don't have an answer ready. But I don't think that sort of thing is directly supported. That might be done possible with more work, but yeah, I'm not sure.
Cool. Thanks. Any other questions? With that, let's actually thank Nishit one more time.